To conclude this lesson, I thought I'd show you how to use Desmos to do all that wonderful stuff that we did by hand just a few moments ago. So you can go to desmos.com, or if you have the app, you can just load it up. And I've gone to the liberty of putting all of the data in here, but I want to show you how to do it as well if you've never done it before. So when you go to this plus button up here, it gives you some choices in terms of what you want Desmos to do. Do you want it to graph a line? Do you want it to graph a table? And so what you do is you would choose table. Now you'll notice that I've added a second table and has changed the x values from x1 to x2 and from y1 to y2 just to differentiate between the tables. And then you can just use your cursor to add in the data points. So I can type in 85, move across to 74, and so on. And I can go up and down those columns to add in those data points. Okay? And so you could do that too. And I would encourage you to do it so you create that muscle memory. Now, what I want to do is I want to take this data and I want to do a linear regression on it. And so I'm going to put in expression because I want to put in an equation for it. Before I do that though, it would be really nice to see where the data is. And so something I can do is I can drag this screen. I can zoom in, zoom out, and you notice I'm still not seeing data points, but that's only because most of them start in the 50s and 60s. If I, zoom out again, pretty soon I should, I hid them, that's why. There they are. Okay, and like I said, I can zoom in. If zoom in, zoom out isn't so great, you can also use this little toolbox tool up here, the wrench, to tell it what you want the minimum and maximum ranges to be for the x-axis and the minimums and the maximums for the y. So you can customize it, which is pretty cool. Okay. Now, if I want to do linear regression, I know that the equation of a line is y equals mx plus b. But when I put in y equals mx plus b, I get some really funky results, and it's got an error symbol here too. Okay. So what we have to do when we do linear regressions, we have to do 3 modifications to the general formula for the regression in order for it to do it specifically for our data. So the first thing we have to do is we have to tell it that it's not just any old x we want it to find the regression of, we want it to be x1. Putting your cursor beside the x will automatically subscript it into x1. And you do the same thing for y, and you say, hey, let's use these y values as 2. So looks better. Okay, but it's still having some issues, right? So the problem is it doesn't know how to set these equal yet. It wants us to do a regression. So there's a new symbol that we have to use, and it's called a tilde, and it's found on your keyboard, either in Desmos down here by clicking on ABC, and you'll see it right here, okay? Or on your keyboard, it is right beside the number 1. Over here to the left if you use the shift key. Okay, so I can go shift here and there it is as well. Well, what's really neat about this, and I'll hide this keyboard for now, is here's the regression line. And it's got the positive residuals, that one's a really big one, okay, but they would cancel out or negate all the negative residuals that are underneath here as well. What's even great about this regression is it actually gives me the equation. It says m is 1.16795, b is negative 22.47, but check this out. It gives me the r value. It gives me that correlation coefficient that I'm looking for, and it says it's 0.893. So let's take a second just to write those down in your notes and compare them to what we had before. So using Desmos, we end up with an equation that reads y equals, well, it says 1.167, so it rounds to 1.17, the same as we calculated in the previous video. And then it has a b value of negative 22.47. And I mean, there's a slight difference here, but they're pretty darn close. The slopes to 2 decimal places are identical. And again, what Desmos does is it gives us this r value. So because it's between 0.67 and 1, we know that in our region for correlation coefficients that this is a strong correlation. Okay, so it highly suggests that there is a correlation between grade 12 marks and first year averages. Okay, So the other thing I want to talk about before we move on to the next lesson is what happens if you accidentally include an outlier in your data set. So let's throw this one in. Let's say you've got a student who in grade 12 does really, really well, has a 95% average, but in first year has 30. Now, there could be a whole host of reasons for that as you get into adult life, when your marks might plummet from grade 12. And this is a very, very extreme example, but it's interesting to see if that could happen. We recognize, therefore, that that is more or less an outlier. What happens if we add it in? So let's go back to Desmos. And see what happens if we add in that data point. So we can go to the bottom of my table here and we can add in 95, 30. Okay? That is an outlier. Now, check out our best fit line. Wow, that outlier had a huge impact on our equation of best fit. Take a look at how our slope has changed. It was positive, it's gone to negative. It's almost equal to 0, so there's no correlation at all. The B value is now positive, and the correlation coefficient is, correlation coefficient is very close to 0. The slope is almost flatlined. So we have to be really super careful when we're looking at outliers. Should we include them or not? But my whole point is here, in a very extreme way, for you to be mindful of how they can impact regression formulas that you might run on data sets when you're trying to find a model to fit the data. All right, in the next lesson, we will move on away from linear regressions into other types of regressions as well.